In the last video, we briefly touched on Hyperopt for hyperparameter optimization for machine learning models. I like Hyperopt because it's a general purpose optimization framework, so you can optimize the parameters specifically for machine learning models or for other types of functions. So that's one of the reasons it's my go-to, is because I use it for machine learning, but for other types of optimization problems as well. But there are a number of frameworks for actually generating the optimal hyperparameters given your data and the type of model that you want to use, such as a random forest or XGBoost or XGBoost, so on and so forth. So really the purpose of this video is not so much focused on Hyperopt, but on the fact that there are ways outside of grid search and randomized search to optimize your hyperparameters. So what I first want to do is go to this web page, which I will link to in the script, that talks about some different methodologies for optimizing your hyperparameters. So of course the classic is grid search, which is basically just a brute force combination of all possible hyperparameters. If you're doing something very simple, this actually may not be a bad idea. Randomized search, as you probably know, randomly searches over points in a distribution provided. So like a uniform distribution or something along those lines, it will choose randomly based on that uniform distribution different combinations of hyperparameters. And I rarely suggest randomized search just because there are so many other ways to more intelligently search a distribution of hyperparameters. So again, really what I want to start off with is the fact that there are so many different algorithms for actually choosing your hyperparameters, and I don't think that grid search and randomized search are actually the best default option. So some of these are available in scikit-learn, such as successive halving. There's something called hyperband, which also combines sampling of resources, in other words, data points. So early on, you may only allocate a small number of data to searching the distribution, and then as you get more confident what parts of the distribution are promising, then you will actually add more data to it. So there are a lot of really sophisticated ways that you can optimize your hyperparameters. There's a Bayesian framework called scikit-optimize. We'll talk more specifically about Hyperopt, which is actually technically not Bayesian optimization, although sometimes it's called that. There's a popular framework called Optuna, which you may have heard of, that provides some good options. There are more esoteric libraries such as UltraOpt. There's one called SMAC3. And again, there are code examples here for how you can actually run and tune models. One is called Tune, sklearn. Again, there are just a bunch of these. There's a framework called RayTune. Ray is good for multi-machine parallelization, but you can still run this on a single machine as well. And then after that, in this web page, we actually get on to like AutoML. There's one called Teapot that's pretty popular as well. So that's a way that you can kind of automate the entire process of figuring out what machine learning framework and model to use in addition to the hyperparameters. But again, that's more in AutoML, whereas we're focused on the specific hyperparameters that we want to use. So again, the big takeaway up to this point is that there are just so many different options for actually optimizing your hyperparameters, and grid search is probably actually not the best default unless you're doing something that's very, very simple. So specifically on Hyperopt, again, the goal is not to explain in detail how Hyperopt works. I will link in the script to this article that provides a really good overview of what Hyperopt does. Basically, at a high level, you can just think of it as a methodology to more intelligently search a distribution or multiple distributions, I should say, to figure out what are the best hyperparameters for your model. Now, one area where Hyperopt isn't necessarily as good at compared to true Bayesian optimization is combinations of hyperparameters. So it may do a really good job of figuring out what's the best max depth for a random forest, but it may not be as adept with the math under the hood for figuring out how that parameter interacts with the number of features that you might choose, in a random forest as well. So if we actually look at the parameter grid, max depth and max features are two parameters that we care a lot about. Hyperopt may not be quite as good given the math under the hood with the combination of these two things, but it can individually do a great job of figuring out what's the best max depth, what's the best option for max features, and so on and so forth. I have found that in practice, it doesn't really matter that much. Again, I like Hyperopt because it's general purpose, so I can really customize it and do a lot under the hood. But there could, again, be other options, and I've used true Bayesian optimization in many other cases as well. And so technically, Hyperopt is a tree-based Parson estimator, and we're not going to get into exactly what that is. You can read the article for that. So anyway, onto Hyperopt. You can see that we have to set up our param grid in kind of a specific way here. And again, we're passing in a specific distribution. So here I'm just passing in a random choice, basically, and then a uniform distribution. One's an integer, and then one's a true continuous space. This is the function that will actually generate the model that we want. It'll train the model with Hyperopt, and you can see in the docstring the different parameters that it takes. There is a lot of boilerplate in this function that I have, and most of that is actually to generate the CSV file of cross-validation scores. So most of the code that's actually needed to optimize with Hyperopt is much smaller than this. But again, if you look at this line by line, most of this is actually boilerplate for cross-validation scores. So what we basically try to do with Hyperopt is minimize some score. So this is a minimization function. So we actually do 1 minus the mean on this because we're actually trying to minimize this as well. So it can get a little bit wonky with that, but what we're doing is basically coming up with our cross-validation scores here. So we're passing in our estimator, our training data, cross-validation, how we want to score this, so on and so forth. And then we just take 1 minus the mean of our cross-validation scores, and that's the function that we actually want to minimize. So really most of this code could go away if we didn't care about actually logging the cross-validation scores. And then really the magic here is in these 3 lines of code. So this is where we're trying to minimize this objective function given our parameter space, and then how many ever iterations we want to do, so on and so forth. And then one thing that we do have to do is we do have to refit the entire model once we find, I should actually word that differently. We need to refit the model on the entire data set after we find the best hyperparameters. If you've done grid search or randomized search with scikit-learn, there's a refit parameter that by default is set to true that will automatically do this for you. But with Hyperopt, you have to kind of manually do this as well. So again, there's a lot of boilerplate in here. But again, this is our model objective. This is a function that we want to minimize. So in this case, we have to do 1 minus our mean of the cross-validation scores based on how we have this set up. And then these are the function calls that actually optimize that. And then we have to refit here at the end. So I just make a very simple synthetic data set and then pass in our arguments to train model with Hyperopt, and we can run this. And we can see that, yep, it actually ran. It produced the CSV of cross-validation scores. It saved the model as a pickle file. So we do that here at the end, and we have a model that we can use. So we can see that it kind of spit out some diagnostics for us. So our CV scoring was negative mean squared error. Things can get a little bit conceptually weird when you're like, okay, this is a negative, and do I want to minimize this or maximize this? So that's difficult to explain verbally sometimes, but it is the correct choice in our cross-validation that we actually want to take 1 minus that to minimize our objective function. So you, based on your case, you may actually set up Hyperopt a little bit different. But again, what I love about Hyperopt is just how much control I have over this, that I can specify my model objective and do really whatever I want to in here. And again, by default, Hyperopt just minimizes the function, so I need to make sure that I am providing the evaluation to where it will continually drive the score lower as it searches for hyperparameters in this case. So again, I know that was a lot of information, a lot of detail, but the main takeaway is that there are multiple ways that you can train that you can tune your hyperparameters, and it's not just grid search and randomized search.